So this is a look at titrations, just the basic theory, elaborating on what we did during lab at the first of the year. So a titration is simply an analytical technique known as volumetric analysis, where we deliver a volume of a known quantity in the burette into an unknown in a beaker or Erlenmeyer flask. And by knowing or at least understanding the stoichiometry of the two compounds when they react, we should be able to determine the concentration of the unknown in the flask. So normally during a titration, we end up with a pH meter that could just tell us what the pH was. But the normal usage of a titration involves an indicator, which is a chemical compound that reacts based on the quantity of H plus or OH minus and changes color at the right point or at a pre-designed point. Indicators can have various ranges, anywhere from things that are acidic to things that are quite basic. Phenolphthalein is a good example with a pH range change of between 8 and 10, where we could have something like bromothymol blue, which changes around 7. So when the amount of reactants is equal, we say that the equivalence point has been met. When the indicator changes, we say that that is the end point. In an ideal world, you want the end point to be as close to your equivalence point as possible, assuming that that is what you're trying to find. So with a strong acid and strong base, the first thing we should notice is that there is a very, very predefined shape, this S curve. And you'll notice that the change in pH initially is very, very slow, and then a rapid change going to something that's smoothing out. So the strong acid, strong base can be identified because both the top and the bottom are flat, and the equivalence point or the vertical is exactly that. It's just completely vertical. You'll get to a point in the reaction where the acid that's present, assuming you're titrating a base with an acid, or an acid with a base in this case, it'll get to a point where there will be no or very little acid left. And because the pH change is logarithmic, the change will be very, very slow. When the amount of acid and base is exactly equal, you will reach what we call the equivalence point. And in a strong acid, strong base situation, the equivalence point is at 7. Once you pass the equivalence point, it will quickly increase the pH and level off at the top part of the S curve. So in this particular scenario, the equivalence point is at 7. We're talking fractions of a milliliter will be the difference between being down in this range to being up here. Now the next concept here is what happens when you have a weak acid that you're trying to determine the concentration of with a strong base. A weak acid is governed by equilibrium. However, a neutralization reaction is a one-way reaction. So the stoichiometry is very straightforward. It doesn't matter if it's acetic acid or hydrochloric acid, the calculations will be exactly the same in a one-to-one basis. So first of all, what you'll notice with a weak acid is that the starting pH is at least a considerable amount higher. And you'll notice that the lower part of the graph is not horizontal, it has a much more gradual trend. The next thing that we'll notice is that the equivalence point is always above 7 when you are titrating a weak acid with a strong base. And the reasoning behind that is very, very simple. If you have a weak acid, that means that you have a fairly strong conjugate base. that conjugate base will push the equivalence point up above 7. That is the fact that the equivalence point is above pH equals 7 simply tells us that the conjugate base is having an effect. The stronger your weak acid, so the closer it is to a strong acid, the stronger your weak acid, the worse your conjugate base would be. So it's kind of a way to judge exactly how that's going to work. In these particular cases, when you're dealing with a weak acid and strong base, we use phenolphthalein as the indicator because it changes between 8 and 10. So at each point below the equivalence point, the pH of the solution during titration is determined from amounts of acid and its conjugate base present at that particular time. We would use what we call a before and then after graph. And in those graphs, you're not, unlike the icebox, you're not using concentration, you're physically using the number of moles. So you want to know how much weak acid you have and how much strong base you have. You determine which reaction you're dealing with. So if it's a weak acid and strong base, it would be this one. Then you have to determine the concentration of your acid and your base before and after the equation. Using after in Ka for the weak acid, you can calculate H getting the new pH. Later on, we have a very clear demonstration of how this would work. So that will be something that will be elaborated on. The titration of a weak acid with a strong base is something that we have to get used to doing. One of the things that we notice is that down here we have a strong acid, and that strong acid is fairly horizontal. As the acid becomes weaker, or as we go from 10 to the -2 to the -10, we'll actually see the pH curve flatten out on the lower part, and the vertical component will be less and less vertical. If you were to titrate a weak base with a strong acid, you're basically looking at the mirror image of what we just talked about. With a weak base and a strong acid, the equivalence point is always below 7. Again, the conjugate acid of a weak base will push the pH down below 7. In this case, we usually use something like methyl red, but various ones could actually work. Finally, when you have a polyprotic acid or diprotic acid, basically anything with more than one hydrogen proton, you can actually see that you'll get a curve with 3 different lines on it. The Ka values for these can be determined. So one of the things that we will do when you've done your exercise with pH curves is that if you know what the pH is at the equivalence point, so in this case it is equal to 4, then at half that volume, 25, we call that the half equivalence point, we should be able to go over and find out what the pH is at that point. The pH at the half equivalence point is always equal to the pKa, and that is just an effect that we can see with the Henderson-Hasselbalch equation.
So in this section, we're going to have a look at titrations and the calculations that surround them. We've already done the theory, so I think we should now move and talk about what that means when we are in the lab or when we're doing calculations surrounding titrations. This question says, how does the titration of a strong monoprotic or one proton acid with a strong base differ from the titration of a weak monoprotic acid, for example acetic acid, with a strong base with respect to the following criteria? So we have 5 different things we're going to look at. So A, the quantity of base to reach the equivalence point. So in this case, it's the same for both acids. It doesn't matter. This is we know neutralization reactions, acid plus base, are one-way reactions. So whether the acid is strong or weak does not change the stoichiometry of that reaction. So it is the same for both of them. For B, the pH at the beginning of the titration. So a weak acid will not dissociate as much as a strong acid. Therefore, it will not produce, assuming equal molar concentrations for each as a starting point, it will not produce the same number of H plus ions. Therefore, its pH will actually not be as low. So the starting pH is higher for a weak acid. The pH at the equivalence point. So if you are titrating a weak acid with a strong base, the pH will be greater than 7, or basically higher than a strong acid. So strong acid, strong base will have a pH of 7.0 at the equivalence point, whereas a weak acid and strong base will have a pH higher than 7, and if you were to titrate a weak base with a strong acid, you would have a pH below 7 at the equivalence point. Question D. The pH after the addition of a slight excess of bleach. So in this particular case, the pH will essentially be the same. And then finally, the choice of indicator in the two situations. So there is a section in your textbook, and it's figure 16.7, and it has this diagram on it, which has the indicators that you may be familiar with. The indicator we are most familiar with is phenolphthalein, but it has the change point, above where the equivalence point or where the end point is. So we're going to pick an indicator based on where the color change will take place. So phenolphthalein is an awesome indicator for weak acid, strong base, because it goes from colorless to pink. So it's a one color indicator. Whereas basically the rest of them are two color. They go from yellow to blue or red to yellow, depending on the situation. Normally you get better results with color to pink because seeing the change in color from one color to another is more difficult than from color to pink in this particular case. So in titrating a weak acid, one needs an indicator that changes at a higher pH. So we would very much like to use phenolphthalein for the weak acid. If we are going to do it for a strong acid, strong base, we need something that's going to turn closer to 7, and bromothiamyl blue would probably be the best choice there. So for question E, phenolphthalein would be the choice for the weak acid. And something like bromothiamyl blue for the strong acid. So now we're just going to use what we've been talking about to try and determine what the pH range will be, and that could help us make decisions about indicators in the future. So for question 2, we are being asked to predict whether the equivalence point for each of the following titrations below is below, above, or at the pH equal to 7. So we're also going to try and explain as to why this is the case. So first of all, let's write out the equations. So sodium bicarbonate or sodium hydrogen carbonate, baking soda, plus um, sodium hydroxide will produce H2O plus Na2CO3. Just the skeleton equation is fine. The ratios really are irrelevant. At the equivalence point, I'm going to have two ions. I'm going to have sodium plus and carbonate. Um, Sodium is a cation, so technically it could behave very, very weakly as a Lewis acid, but it's really not going to do anything at all. However, carbonate is the conjugate base in this reaction, so it will actually raise the pH slightly. So, since 3O minus 2 is the conjugate base, Cb, will be above 7. So now we have the next question B. It says ammonia is titrated with HCl. So again, write your equation out. NH3 plus HCl produces NH4Cl. So at the equivalence point, all of this is a reactant, and I have two things present. I have NH4 plus and chloride minus. Now, right off the bat, we know chloride is a conjugate base. It's the conjugate base of hydrochloric acid, which is a strong acid, so it does not affect the pH very much at all. NH4 plus is the conjugate acid of the base ammonia, so it will actually cause the pH to be lower than 7. So, since NH4 plus is the conjugate acid, Ca, below 7. And then finally we have potassium hydroxide being titrated with HBr. So HBr is one of our 7 strong acids. KOH is a hydroxide with a group 1 cation. So that means that it is also a strong base. We have strong acid, strong base. So KOH plus HBr produces water plus KBr. So bromine is bromide is the conjugate base of HBr. It is a strong acid, so this is not going to affect us at all. And for the same reasons that sodium didn't affect us up here, potassium will not affect it really at all. So there's little effect. The pH should be about 7. So that's how it works. So two monoprotic acids, both with 0.100 moles per liter in concentration, are titrated with 0.1 moles per liter sodium hydroxide. The pH at the equivalence point for HX is 8.8, and that of HY is 7.9. Question A, which is the weaker acid? So the pH is determined the pH at the equivalence point is determined by the identity and concentration of the conjugate base, whether that's X minus or Y minus. So we have our X, it could be X minus or Y minus. The higher the pH at the equivalence point, the stronger the conjugate base must have been. The stronger the conjugate base, the weaker that acid must have been. So HX is 8.8. HY is 7.9. That means that X minus must be a stronger conjugate base to make the pH higher than the HY. To have a stronger conjugate base, that means its acid pair was weaker. So which indicators would you use for these acids? So we have Hx and Hy. The equivalence point for Hx is 8.8 and Hy is 7.9. So 8.8, which is going to be in here, um, basically could have been thymol blue or phenolphthalein, but it looks like the color change for phenolphthalein is going to be a little bit better. For Hy, since we're at 7.9, so we're just below here, we're basically going to have to pick something that's as close to that as we can. And thymol blue isn't going to change until after, so we're probably going to want to pick this here, which is bromothymol blue. So you have to pick the range as which is going to give you the best or most accurate results. So since Hx changes at 8.8, we will use phenolphthalein. And at 7.9, the best choice on that list is bromothymol blue. And you can find this chart, depending on which textbook you're using, on those pages there. So now we're going to start getting into calculations specifically with the titration. So we have a question here that says assume that 30 mils of a 0.1 molar solution of a weak base, let's call it B, that accepts one proton is titrated with a 0.1 molar solution of a monoprotic strong acid, HX, so something like HCl. How many moles of HX have been added at the equivalence point? So the word equivalence tells you what the answer is. So at the equivalence point, the moles of HX must equal the moles of B initially present. So 0.10 moles per liter times 0.300 liters equals 0.0030 moles of HX added. So the word equivalence means that they are equal, so that's how you solve that first one. What is the predominant form of B at the equivalence point? So we have base plus some acid. It's a neutralization, so it's a one-way reaction. So the predominant form is BH plus, which is the conjugate acid of B. What factor determines the pH at the equivalence point? So there's really two things that we're really focusing on. The most obvious one is the Ka value for BH plus. That will determine it, which again could be, if we knew what the Kb is for B, we could figure out what the Ka is for that. So if we had ammonia NH3 and this was NH4 plus, we could just take 1.4 times 10 to the negative 14 and divide it by the Kb for ammonia, 1.8 times 10 to the negative 5. So that's the biggest part, is the Ka. The second thing that's going to really affect it is the concentration of pH plus. The more of that there is, the lower the pH will be. So it's those two things that will really affect us at the equivalence point. So basically the moles of BH plus produced divided by the volume will give you the concentration. And if you have the Ka, you can use an icebox, or you can just use the equilibrium theory that we've been using to solve that. Which indicator, phenolphthalein or methyl red, is probably the better choice for this titration? So we have a weak base with a strong acid. That tells us that the equivalence point is going to be in a situation where the pH is less than 7. And that pH is going to be less than 7 because BH plus is now present. So we need something that's going to be just below 7. So we take our sheet, we find 7. It's not bromothymol blue would be good for something at 7. So we'd want something a little bit below that. So I think we're at the methyl red range. And that's what this is, methyl red. Again, look at that diagram in your textbook. So methyl red, since the pH at the equivalence point is going to be less than 7, and we know it's less than 7 automatically because it is a weak base with a strong acid. So question 5 brings us to really one of the most important calculations we do in titrations, and that is calculating the pH at various points along a titration curve. So the question says, consider the titration of 30 mils of 0.030 molar NH3 with 0.025 molar HCl. Calculate the pH after the following volumes have been added. So right off the bat, I hope that we've realized that ammonia with its lone pair is a weak base, and it has a conjugate pair of NH4 plus. But more importantly, the Kb for this acid is equal to 1.8 times 10 to the negative 5. So we have a lot of work to do for each one of these. This is a relatively tedious process, but it's very repetitive as far as the calculations work. So when no volume has been added, we are literally just looking for the pH with 30 mils of 0.030 molar NH3. So we know at equilibrium the concentration of O minus is going to be some unknown value, which we can use our icebox to determine. And I'm not going to write out the icebox every time, just because that's a lot of extra work, and I know we know how to do that at this point. I also am going to make an assumption that the initial concentration of NH3, which is 0.030, is not going to change appreciably due to the loss of X. So I'm going to ignore X. 0.03 divided by 1.8 times 10 to the negative 5 isn't a super big number, but it's enough for me to make that assumption and make my work a little bit easier. So NH3 is equal, the concentration of NH3 is equal to 0.030. And we could write minus X, we could go along and do that, but we're not going to worry about it. And we also know that the concentration of NH4 plus is equal to X. So the equation that I'm getting this from is NH3 plus H2O is in equilibrium like this, where we have liquid water being produced. So I have the Kb, and that's what this is going to go into. So I have 0.03 moles of this. I don't know how much of this I'm going to produce. So the Kb for this expression is the concentration of OH times the concentration of NH4 plus over the concentration of ammonia. That is the Kb value that we have up here. I don't know what these are, so X squared and in this case X is equal to 7.348. And again, I expect that you're able to solve for those X's based on what we've done already. The pH is equal to 14. Take away the negative log of the OH concentration, or the POH, 7.348. And the pH of the solution before we add anything is 10.87. So that's just a general equilibrium question where we have a concentration of an equilibrium um, expression. We use the icebox to solve the pH, ignoring the loss of x due from the initial, just because we believe that that is going to be relatively small. So now we get into the next part of this, which is going to be repetitive. So we'll take some time doing it with the part B, and then we'll speed it up for the parts C through F. So we are now doing a neutralization reaction between ammonia, so NH3, plus a strong acid, HCl, and that's going to produce NH4 plus Cl minus. So we're going to use this reaction every single time, and we'll use a before and after to help us get organized here. So the before, we have 30 mils of 0.030 molar. So in the before and after box, when you're using those, you're using moles, not concentrations. So first we're going to get the number of moles of NH3. So 0.030 liters times 0.030 moles per liter NH3, and we get 9 times 10 to the negative 4 moles, and that is NH3. So I start with 9 times 10 to the negative 4 moles of NH3. That's going to be the same number every single time. Next, I have a volume of unknown concentration. So that's where this comes in. So this is the only real difference in all of these calculations. So I have 10 milliliters of a 0.025 moles per liter HCl concentration, and that's going to give me 2.5 times 10 to the negative 4 moles of HCl. So 2.5 times 10 to the negative 4. And I assume I have none of that yet in my solution. So now we have a one-way reaction. So you look at these two. They're 1-to-1. So you look at which one is less if it's 1-to-1, and it's this one. So now you know that this is all going to react. This is your limiting reactant. And it's going to use up the 2.5 times 10 to the negative 4 moles of itself, leaving itself with 0. But because it's 1-to-1, it's got to use 2.5 times 10 to the negative 4 moles of this. So we're going to lose that. So 6.5 times 10 to the negative 4 moles of ammonia would be left. This is going to produce 2.5 times 10 to the negative 4 moles of this, and 2.5 times 10 to the negative 4 moles of the chloride ion. Well, we're now basically in a situation where we can use the Henderson-Hasselbalch equation if we want, because we have a base and the conjugate acid, or we can do it out a different way. So I'm going to go concentration of NH3 now is equal to 6.5 times 10 to the negative 4 over the volume. So you got to watch and be careful that you had 30 mils of base, and now you've added 10 mils of the acid. So your total volume now is 0.040 liters, or 40 milliliters. And the concentration is now equal to 0.01625 molar. The concentration of NH4 plus is 2.5 times 10 to the negative 4 over the same volume, because they're in the same flask. And that's 6.25 times 10 to the negative 3 moles per liter. Finally, we have to figure out what the Ka is. So Ka is equal to Kw divided by Kb. So now we're just going to fire it into an expression. So the concentration of H plus, we're just going to rearrange our Kb expression from up here. We'll rearrange it for we'll set it up for the acid side, and then we'll solve for H plus. So H plus is equal to Ka times NH4 plus over the concentration of NH3. Solving for H plus just allows us to go directly to pH. So that's equal to 5.56 times 10 to the negative 10 concentration of ammonium equals 2.14 times 10 to the negative 10 moles per liter. The pH then is equal to 9.67. So we're going to streamline that going forward, but as you can see, we've added 10 mils of an acid, so the pH has dropped some. In the meantime, we have created a buffer though. So now we're going to repeat that exact same process we just completed, but we're going to use 20 mils of acid instead of 10. So NH3 plus HCl So we start with the same number of moles each time of the base, 9 times 10 to the negative 4. We have to recalculate the amount of HCl that we use. So I'm not going to show this each time, but it's the volume in liters, so 0.020 liters times the concentration of HCl, which is 0.025. So the number that I'm putting in here is just the product of volume times the concentration of HCl, which in this case is 5 times 10 to the negative 4. Assuming we have none of this, look at it. This one is smaller, so it's the limiting reactant. I will have none of that left. Be 5 times 10 to the negative 4 on both sides. We're now just going to streamline the H plus is equal to Ka times NH4 plus over NH3 is equal to 5.56 times 10 to the negative 10. So the only thing that could be a little hurdle here for us is just making sure that we're putting it into concentrations. So 5.0 times 10 to the negative 4 divided by the volume. So with 20 mils, it's 20 plus the 30. So we're going to put it in as 50 mils. The amount of ammonia is 4.0 times 10 to the negative 4 divided by the volume. And the concentration of H plus is 6.94 times 10 to the negative 10 moles per liter. The negative log of this number gives me pH 9.16. So the pH continues to drop. we are going to keep repeating this process. So you can see the pH is gradually changing, and at some point we're expecting it to move into a rapid change to create that S curve that is typical of a titration. So we're just going to adapt now and do 35 milliliters. So NH3 plus HCl, one-way reaction, NH4 plus Cl minus. We have before and after, 9.0 times 10 to the negative 4, 0 and 0. Recalculate the amount of HCl, so 0.025 molar HCl times 0.035 liters, and that will give us our new concentration, and we end up with 8.75 times 10 to the negative 4 moles of HCl. We now recalculate, look at them. This one is still smaller, so that's my limiting reactant, leaving me with 0. That means that there is going to be only 0.25 times 10 to the negative 4 of that left. This number moves down to here. We now calculate for the concentration of H plus. Remember that we have to correct for the total volume. The total volume is 65 milliliters now. And with this calculation, you get 1.946 times 10 to the negative 10 moles per liter. Turn that into pH. So this is to the negative 8. And we turn that to pH, and that's 7.7. So now we move on to 36 milliliters, which is a number that was picked because this is probably the equivalence point, because we're getting very, very close above. So we do our before and our after. 9.0 times 10 to the negative 4. If we recalculate 36 milliliters times the concentration of HCl, you will find that this is the equivalence point. Assume we have none. This will completely react all of this, meaning I have 9.0 times 10 to the negative 4 of just the product, so there is no reactant left in this case. Now we really can't do very much because we don't have any of this produced. So we will now create an equilibrium with NH4. And so this is a little bit different because of how this has to work. So Ka is equal to the concentration of H plus, the concentration of NH3 over the concentration of NH4 plus. So remember that basically we're just ignoring what's happening here, and we're assuming that we have NH4 plus dissociating into NH3 plus H plus. And I'm going to take this equilibrium, and this is only true for the equivalence point. I'm going to take this equilibrium and use it here. I don't know how much of this, I have none of this to start with. I don't know how much H plus I have, but I do know what my starting material is. So this is going to equal x squared over remember, you have to work with concentrations. We'll assume that the loss of x is insignificant. And this whole expression is equal to 5.56 times 10 to the negative 10. So multiply this by that and take the root of it, and we find that X, which is equal to the concentration of H plus, is equal to 2.75 times 10 to the negative 6 moles per liter. Take that concentration of H plus and find that the pH is equal to 5.56, which is what we expect. A weak base with a strong acid will have a pH lower than 7 at the equivalence point. Finally, we are at a situation where we're going to go 1 mil past the equivalence point to see what happens. So we start with our equation again. Is an equation where we can have before and after. So before, as always, multiply 37 milliliters by the concentration of HCl, and you'll get 9.25 times 10 to the negative 4. So for the first time, the amount of HCl is now above the base, assuming we have 0. So now when we compare them, this is the limiting reactant. So this becomes 0. That leaves me with 0.25 times 10 to the negative 4 moles of HCl remaining. And 9.0 times 10 to the negative 4 ammonium, and 9.0 times 10 to the negative 4 chloride present. So now we're in a situation where we just have HCl present, and that's really where our pH is going to be. This is a strong acid, and we could do the same if it was a strong base titrating a weak acid. That is going to be where our pH is coming from. So since HCl dissociates completely to hydrogen and chloride, we know that we're going to have 0.25 times 10 to the negative 4 moles of H plus, and we know that that's going to be in 0.067 liters. So the concentration of H plus is equal to 3.731 times 10 to the negative 4. That's in moles per liter. Take the negative log of that number, and we find that the pH is equal to 3.4. So you can see how quickly the pH is now going to drop after we go 1 mil past the equivalence point. So now that we've looked at how pH can be calculated throughout a titration, we're going to look at how we can calculate the pH at the equivalence point of a solution. So the question says calculate the pH at the equivalence point in titrating a 0.100 molar solution of each of the following with sodium hydroxide. So hydrobromic acid. So hydrobromic acid, I didn't give the equation there because this is HBr. HBr is a strong acid, and that strong acid is going to completely react with NaOH, producing water and basically a salt of sodium and bromide. So we know that in this particular case, we're ending with HBr plus NaOH to give H2O plus NaBr. So there's not a lot here. We know that bromine or bromide is a conjugate base of a strong acid, so it's not going to affect the pH. And we know that sodium is an ion of +1, a very small ion with a very low effective nuclear charge. So it's not going to do much as far as becoming a Lewis acid. So the pH here is basically going to be 7. We know that before we even do any calculations. So the neat part here is we can figure out what the concentration of the salt on these reactions is going to be no matter what. It's going to be an approximate calculation because we're going to take a couple things into account, but hopefully it'll make sense. So we're dealing with the equivalence point. So we know at the equivalence point, the concentration of the acid needs to be equal to the concentration of the base. So that means that the volume of the acid times the molarity of the acid needs to equal the volume of the base times the molarity of the base. So if the concentrations are equal, then we're assuming that we have equal volume. But if the volumes aren't equal, what really matters at the equivalence point is that the number of moles are equal. So we're saying that the number of moles of the acid needs to equal the number of moles of the base here. We can rearrange and figure out what the volume of the base would be. So the volume of the base is equal to the volume of the acid times the molarity of the acid divided by the molarity of the base. And that's going to equal 0.10. I know what the acid's going to be. It tells me 0.100 times the volume of the acid over the concentration of the base, which is given to me, 0.080 moles per liter. So divide this by this, and I get 1.25 times the volume of the acid in every situation. The total volume is going to equal the volume of the acid plus the volume of the base. So if I substitute this expression in for volume of the base, I get V acid plus 1.25 V acid. And that gives me, so V acid plus 1.25 V acid gives me 2.25. So the total volume is going to be, you have to equal 2.25 times the volume of the acid that we used. Again, this is kind of neat. So the concentration of the salt, which we're talking about this, has to equal the number of moles divided by the concentration. So we end up with the moles of acid times the volume of the acid divided by the total volume, which is 2.25 V acid. This gives us 0.100 because V acid is going to cancel out, and we know the molarity of the acid is 0.1 divided by 2.25 equals 0.044 moles per liter. So the concentration of all of these solutions where we're talking about salts is going to be 0.044. It doesn't matter what we're doing because we have defined concentrations of our solutions. And like I've already talked about, in this case, sodium ion and bromine ion, neither of which will affect the pH. The pH then is going to be equal to 7, a strong acid and strong base. So in part B, we're going to treat the lactic acid as the conjugate acid of the lactate ion. And the reason for doing that is simply because we know what the concentration of that salt will be, because all of the salts will start with this particular concentration. So we can assume that the lactate ion is going to be A minus, and its conjugate acid will be a HA. So A minus plus H2O is in equilibrium, giving me HA plus OH negative, where this is lactic acid and A minus is the lactate ion. I know that the Kb for this process is equal to Kw over Ka. It is 7.14 times 10 to the negative 11 in this case. So by doing this, what we should be able to understand is that the concentration of water, first of all, doesn't matter. But by doing this, we know that the concentration of HA and OH are equal to X. And we know that the starting material is 0.044. And we know that from the work we did up front. There's no difference at all between any of these questions with that. So this is going to be X, and they are equal. So Kb is equal to the concentration of OH minus times the concentration of A minus all over the concentration, HA, all over the concentration of A minus. It's the Kb expression. So rearranging for this equation for X is very simple. So X is equal to, this could be X times X, so X squared. It's going to be Kb times A minus. We will assume that the loss of X from the 0.044 is negligible. And X is equal to 7.14 times 10 to the negative 11. And 0.044. And I have this at 1.78 times 10 to the negative 6. X is equal to the concentration of OH negative. So POH is equal to 5.75, making pH equal 14, take away 5.75 is equal to 8.25. There are different ways to do this equation, to work your way through it. This is just one particular method that will produce an answer that is what we expect. So 8.25 is the pH when you have a weak acid with a strong base, which is exactly what we expect. So sodium hydrogen chromate is the same idea that what we've talked about before. It's the chromate ion plus H2O. We're going to do exactly the same thing. We're going to talk about the base, HCrO4 minus plus OH negative. We know what the salt is going to be, 0.044. We know that this is going to be X, and that doesn't matter. Just writing the equilibrium line for the icebox. We know that there's a minus X here, but we will ignore it in this situation as well. Kb for this expression is equal to HCrO4 minus concentration OH negative over CrO4 minus 2 is the chromate, where Kb is equal to Kw over the Ka for this process. If we look it up in the textbook under Appendix D, we get the Ka for chromic acid at 3.0 times 10 to the negative 7. So the Kb is then 3.33 times 10 to the negative 8. We're going to do exactly what we did up here. There is no difference. The concentration of OH negative is equal to X, which is equal to the root of the Ka. So we know what the concentration of OH negative is now. Take the negative log of it. Take the negative log of it and get your POH. So your POH in this case is 4.415, pH is 14 minus the pOH. pH is equal to 9.58. So again, there are multiple ways to approach this this problem, this question. This is just one way. Basically, what we're looking at here in these types of equations, that I'm taking the conjugate base of the acids that we're the weak acids that we're conjugating with, so conjugate we're reacting with, and I'm using them in the hydrolysis reaction. So the conjugate base of lactic acid would be lactate. I'm putting that in the hydrolysis reaction. You finding Kb by taking Kw and dividing it by the Ka. Then just solving for OH. When I get pOH, I solve for pH. So it's a pretty valid and simple method for determining the pH at the equivalence point.